All right. So from the video here, this should be the next example in our notes here. So let's go with it here. So the radius of a sphere is 50 inches with a possible error of, just because we are measuring stuff with measurement tools, right? We have a measurement tool that is very precise. It is 0.02 of an inch. I think that's pretty cool. But there's still air in it, right? Okay, so estimate the possible error of the computed volume. So if we're going to be off by 0.02 inches on our radius, how much are we going to be off by on the sphere of the volume itself, or the volume of the sphere? Let's go with it here. So let's do something. 3.02. Interesting. Yes, you probably could. Yeah, you could solve it for the bottom value, solve for the top value, get the difference in the middle, and then let's do the calculus way. So this is 0.02 off to the right, 0.02 off to the left. And all we're really just trying to do is just trying to figure out that value right there, right? How much are we off by? Trick stuff. Okay. Boom. So that's what we're trying to do. We good? Graphically illustrated. So let's go with it here. This guy is volume of a sphere. And I'm trying to find my notes. Last week. All right. And then we take the derivative with respect to r. Are we okay there? Then let's go with dv is really all that right there. True.
For the last bit, you did. Oh, you changed it to the times dr. Was that to find the error thing?
Say that again.
So for like the last one, why did you multiply it by dr?
We'll see in just a second. Just waiting for people to write it down. Are we done? Are we good? Boom. Okay. Well, let's jam with it here. So there it is. At our dr.
Any questions that put that on squares?
4 pi r squared. Yeah. Uh-huh. All right. And with that, are we good? We are going to get a cubed in there, right? Because the r squared is squared, but then the unit value dr still has the derivative in there. I'm just trying to find it. Because of the little plus or minus 2 at the end there. Okay, mine is different. Plus or minus. So the dr, right, which stands for just the difference, right? So we're technically looking at the error. Essentially looking for the difference between the true actual one, right, and then where it can err on. Sweet. Okay. So on the homework, you guys are going to have something called relative error. And did you guys do this in physics? No.
We did something that was like.
We did like the one that's like experimental minus.
Okay, theoretical or actual? Uh-huh. Okay. Okay, gotcha. So relative error. So what we do here is we just figure out this little piece right here. So relative to, oh, sorry, I went a little bit too far here. So the question is, how much of an error is it in regards to the original base value? That's what we want. So notice it is the derivative on top and then the original equation on the bottom. And then I don't like the little 3 on the bottom over there. Can I just multiply through by 3 everywhere, top and bottom, just to get rid of 3? I don't like fractions inside fractions here. So I do this, and then I can kind of see how things are going to be simplified further. All right, I got myself, let's see, 12 and 4. That's gone. The pi's are gone. And the radius is still there.
3 doctors.
Cool. All right, and almost there. All we got to do is put in our error again. And remember, our radius was 50 originally, is that right? And so here's what we do. We get ourselves that value there. What does it mean? Absolutely. So if the radius was only 1, this error would be ginormous. We good? And it really is because of that 0.02. But notice real quick here, technically it's this. It's the 0.02 compared to the radius of 50. Essentially, that's what you're doing, is you're comparing these two here. If this was 1, that'd be a huge error. This is 50. This was 50 million. There's hardly any error at all, right? Just because bigger of the value itself here. So Adrian says, what does it mean? It means this. It means the percentage error is right there. Okay, we good? So we move the decimal place over. Second. Okay, let's see.
Well, if it's flat to like, we divide by 250.
Let's see, is it be 0. Okay, let me just check on the calculator here. Anybody check on the calculator real quick here? What is 0.060?
Add 2 zeros, and multiply it by 2 either way. If you multiply both sides by 2, and it's 0.12, and then divide it by 100, so it's 0.00. Because you could change that to 6 over 100.
Yeah.
Yeah, we're good there.
Yeah.
I did 50 times 50 is 250.
Gotcha. Okay, no problem. All right, so here it is. So how much error do we have? We have less than 1%. We have almost like 0.1% of an error. We're good? That's cool. And then the question is, how much error do you tolerate based upon whatever you're doing, right? If you're building a house and 2x4s are coming across, you could be a little bit off, right? If you're building a little thread for a tiny, tiny little bolt that goes into a car that is specified, that needs to be like super, a lot less air on it, right? But it's kind of crazy, guys. You guys think of like when we go to the store, like buy like screws or bolts, right? They're not perfect. We good? There's a little bit of air in them, but then what it goes into usually has a little bit of air and give as well. So then they fit perfectly together, right? So that's kind of like a cool thing. Maddie.
What if you do the zeros?
We just moved them over because we're going from decimal to percent. So we just move 2 decimal places over to the right to create the decimal. Oh, sorry, to create the percentage, right? All right, and that was the end. Are we good? So that was the end. Let me jump to the next one since we want to finish up all. Okay, now we're gonna have. Okay, Lila, this should make sense from the beginning now. So 211, last part here of chapter 3 is called hyperbolic functions.
You can move on this one.
Oh, really? Interesting.
Made a little piece of paper, folded it up in a way and phrased it.
Oh, that is so cool. Okay.
I have a plane right in the middle, it's just a single point.
Uh-huh. That's cool. So let's do this here. So they're actually going to be hyperbolic trig functions. Ooh, your next level here. Okay, so let's go back to what we remember about trig functions. This has been a while. So what we did in trigonometry was something called circular trig functions. How come it was circular? Yeah, it was based upon a unit circle. That was it. Ours was equal to 1, and then we went around, and then we had a t value. T value was just interesting. It was just the length away from 1, 0. Is that right? To the top. And then we could take t as a length around the unit circle, or we could also think of t as right the angle measurement right inside the area. That's so cool. And then we had one specific trig function here that kind of helped us out, right? Remember the Pythagorean theorem? And the trigonometric Pythagorean theorem was anybody? Perfecto. Awesome. Okay. So those are called circular trig functions. Neat. We're going to go into a little explanation of them as well. And then we'll do them. But I think we should be able to get through all of it here. All right. Let's jam the other way. So that is a circle. Let's jump this way. This guy is called a hyperbole or hyperbola. Right? Hyperbole is English stuff. Yes. Hyperbola is math stuff. Okay, so now let's talk about this. This is the craziness about it. So, how do we define a trig hyperbolic function? We go like this. We go a little point over here. And the only thing is with hyperbolic functions here, we remember, especially if it's 1, and if this guy's a square, there's a perfect square in the middle, the hyperbola equation is x squared minus y squared equals 1. Are we good? So we have changed our Pythagorean theorem equation. It's no longer Pythagorean theorem. It is like a hyperbolic equation. Okay, the only thing that we're going to think about is the fact that x has to be greater than 0. It has to be on the right side. So we're going to do this. We're going to scratch that one off completely. We're good? So we only use when x is greater than 0. So x will always be positive for us. Interesting. Okay, so hold on. X is positive? No, we'll see. Okay, so let's define. This guy is going to be, oh, interesting. It's COS with an H after it. So it's Kosh. And then, I don't know, Sinha. So instead of saying Sinha, well, we normally just would say cinch. We had a little cinch. We had a little CH at the end as opposed to just a regular H. Kosh and cinch. It's a cinch, guys. Okay, so how do we define this here? We take a line back to the origin, and what we do is we fill up the area. And that area is going to be t divided by 2. Crazy at first. Get it just a second here. Okay, and this would be the hyperbolic trig function. So that's weird. Okay, so on the circular functions in trigonometry last year, we defined it to be connected to the angle measurement. Is that right? Here with the hyperbolic functions, we are connecting it to the amount of area that you have. And the amount of area that you have is half of t. Megan.
Are all the sides of that blue triangle straight, or does it like go?
No, it curves.
Say again, say again. Sorry, I didn't get it. What you were saying.
Area of view. Is straight or is that like?
Oh no, so it's curved on one side, right? Yeah, there's a straight line going from the dot to the origin, straight line going from 0 to 1, and then there's that little curve that happens. Whew. Okay. All right. I do want to show you a little something though. Let's see. Um, it's not new because the fact is not a new thing. So let's go back. Let's just out of curiosity here. We have a little bit of time. Let's go back to our circular function and just out of curiosity. That's so funny. Um, let's go back to our circular function and let's do that in terms of area. We're good? Just kind of a crazy thing. Right? So circular function, here it is. And then I need to know what is the area of T and just see what happens here. We're good? So let's think with me here for a little bit. So do you guys remember area of the sector formula? Yeah, it was. Of course, everybody remembers it. It's 1/2
What is that?
r squared times the angle measurement or theta. Perfecto. Okay. So if I were to put this in, and I would have an r value of r value of 1, is that right? Don't we have r value of 1? Right? Because that's a unit circle. True, true. So if I put a 1 into there, and my angle measurement is, what is my angle measurement? T. And if I do that, do I get the same exact angle area? That is so cool. So we actually have been defining it in terms of this. We just never wrote it as t divided by 2. But it all works out exactly the same way. Okay. Are we good? Does that make sense?
Very much so.
Awesome. So it is really the same definition, right? We just define it differently, but we can use the same definition for this one as well. It's half of the area that was there. Cool. Okay. So then let's do some. So this is, I think, from your textbook, or I got it somewhere else. I thought that was kind of cool. So there it is, guys. So remember in trigonometry class, I think, or probably an algebra class. I think his algebra class was because Mr. Grant, I walked in one time when he was teaching it. So between two different poles, like um, Golden Gate Bridge or something like that, right? We have this little bar that sways down, right? And then comes back up. We can model it with a polynomial. We could model with polynomial because polynomials can model pretty much anything. That's what we use them for. But technically, if you want to take a look at it, the best model for it is called a Cantory. So that little pink line right there, to perfectly model this. Because notice it almost becomes flat right here. We're good? It's not like a parabola where it kind of comes down. You can expand out a parabola twice, right? But it still doesn't kind of fit it just perfect. So there it is. So it says in engineering, whenever we encounter light, velocity, electricity, radioactivity, we think about hyperbolic functions to model that behavior. So in this case, the famous application hyperbolic function describe a hanging wire. Any hanging wire can be proved by a very flexible cable, such as a telephone pole, power line, whatever. It is the shape of this equation right here. Y is equal to C plus A cosh X over A. And it's called the Cantory. We're good. And then, of course, here it is. Another application is hyperbolic function is the waves. So if we look at the velocity of water, how fast water is moving, especially if there's waves along the ocean floor, there's that equation right there. It is a hyperbolic function with tangent inside it. Okay, we don't say tan ha. We pretty much just say hyperbolic tangent at this point. There's no fun names. Just Kosh and Cinch are the only ones that have nicknames to them. Okay, so how do we produce this? What's going on here? So if we were to graph, let's go back real quick here, put things together, and then we'll kind of. So if we go back over here and we take, let's do the sine function. So cinch first, and we're to graph cinch on an X and Y grid. So good. It's going to look like this. And I think there's my cinch value. We good? It goes negative at 0. And then we notice these two lines right here, this one and this one. these two become our asymptotes as we go up. And the funny thing is this. There you go, the great finale here. Ready? With this, if you were to add the two asymptotes together. We're good. So you got asymptote on one side, asymptote on the other. You add these two asymptotes together, and it gives you the exact equation for the trig function. That's crazy. And it works just perfectly. So it's 0, 0, it's actually 0. And so the two asymptotes come together to give us our trig function formula. Then we do the same for cosh. So important if you want to write that equation down, that'll be good. Yeah. So the equation that we use for sinh. All right. And then let's go with cosh. Right there. There's our two asymptotes going on each side. Cosh, remember, x is always positive, right? So x will never be negative. Notice it comes down to 1 again. And there it is, our two asymptotes. But if you were to add them together, subtract them and add them. Sorry, guys. Are we good there with this one? This was the subtraction part, right? These are subtraction. This is the addition part. So if you're to add these guys together, you get the exact perfect equation for that red line there. Okay, so we're going to use them. How about the others? The others are just defined based upon those. So yes, absolutely. So hyperbolic tangent is sinh over cosh. We're good? There's our other ones here. And so they all work out exactly the same. We define them to be exactly the same, right? By definition. So we're defining them. So I'm going to have you guys write down a couple of things here. First of all is the definitions of each one. So algebraically, we only define sine, sinh, and cosh algebraically, right? Everything else is defined based upon those two. All right, then we got some properties that work out as well. So we know one of the properties is the hyperbolic form, right, of our Pythagorean. Okay, we're good there. People still writing, no problem. Okay, so that's the definition. That is how we define them to be. We good? And that's our choice of how we do it. All right, as soon as we make that choice, then we have properties that come along. Now, I'm going to do that real quick here. With trig class, we took a long time to establish the properties. I'm just going to list them for you. We good? So if you guys can just write them down on the list right there. So what does the first one say? Sinh of -8, negative x is negative sinh of x. Do you guys remember that is something called the odd property of sine? Remember that? So hopefully you guys do. Right? If the value is inside is negative of sine, we have to take it out on the outside because sine are odd functions. Cosh even function, right? We can drop the negative sign. And we saw those by the graphs themselves. Can I go back real quick here to the graphs? An odd function right here. They should be symmetric about the origin, right? Even function, they symmetric about the y-axis. So let me just jump real quick here. I know you guys are writing it down. So boom, boom, boom. There it is, right? That is an even function, is that right? Boom. And then this guy, odd function. Whatever's in quadrant 3 is reflected in quadrant 1. Okay, let you guys finish writing out the identities, and then we'll work with them. So I don't think cosh squared x minus sinh squared x is equal to 1. I don't think we call that a Pythagorean theorem, I didn't, but I'm not sure. I'm not sure if we do or not there. All right, and then if we think about this here, do you guys remember, anybody remember from trigonometry? Was sinh or sine of x plus y, was it sine of x cosine y plus cosine x sine y? Was it different?
Yeah, of course.
Okay, cool. Kara says sine and sinh are the same for their addition of angles. How about cosine? I got my trigonometry book right here. 1 second, let's see. Oh, it's in that. So, addition formula is the same for cosine. Oh yeah, for cosine, the sign is different. So this guy here, it used to be a minus for our trig functions. Now it's plus. Okay, so yeah, so slightly different there. Okay. Okay, so 25 minutes left. Let's go with it here. So we need to do some algebra. We need to move, then we need to do some calculus here. So in the homework here, something about this here, some algebra stuff. Can we prove that this is true? And how do we prove? We have to go back to definitions. Is that right? So what is the definition of cosh squared x? Or just cosh of x? Yeah, it's the algebraic formula e to the x minus or plus e to the negative x over 2. And we're going to square this guy. We're good. Then we're going to subtract e to the x minus e to the x negative x over 2. I forgot a little square. There should be a little square over there. And the question is, can we prove that to be true, right? So there'll be just a quick review of for algebra stuff. Then, Ava, I'm so sorry. I got stuff here. Didn't see it. All right. I'm going to give you a little bit of help here. This one is if we were to FOIL this out, just to simplify the form here. That little piece right there. So I'm just moving off to the side just to FOIL things out. So e to the x plus e to the negative x. And see, I'm writing in my little 2 there. There should have been a 2 right there. Like that. Okay. If we're to FOIL this out, that means we have this times another one of these. Is that right? And so we FOIL x to the e to the x times e to the x makes e to the x squared. Plus this times that, which we'll see something very interesting with that. This times this. Everybody agree there? And at the end, there'll be one of these being squared. There's your expanded form. All right. And then we know something about exponents. If we say e to the x to the 2, we can just say e to the 2x, right? It's a multiplication between the two exponents. And then e to the x times e to the negative x. What is that going to happen? What's that going to do?
X minus x equals 0, just 1.
1. Are we good with 1? Those are just going to cancel themselves out. The other is going to cancel themselves out as well. And this is going to be e to the negative 2x. So if we were to write this out, this becomes e to the 2x plus 2 plus e to the negative 2x. Are we good there? Just algebraically, that's all. All right, can you guys do the other one? Can you guys do e to the x minus e to the negative x? I don't think I did that on my slide here. I'll let you guys try it yourself here. I'll show the answer on the next slide. And some people just kind of do it by like, oh, I know the difference real quick here. And once you do that, can you expand it out? So the next line, so this next line right here should go underneath over there.
It was over 4.
So yeah, over 4. Yep, everything's over 4. So tell me if you guys agree here. So the expansion would be this, what we did before. And this would be the one with the minus in there. So the only change here is we would be a -2 instead of a +2. And so we're just trying to see if it still equals 1. We can break it up into each of the pieces being over 4. That's probably the easiest way to do it. And then we're going to distribute that little negative to each side as well. And then can we cancel stuff?
I see. Oh, the rest is I understand.
Perfect. Okay. So that guy will cancel this one. Is that right? This one. And then we have 2/4 plus another 2/4. Perfect. Okay. So algebraically, we've proven. Oh, do you guys remember what is that? QED. Awesome. There it is again. Okay. So that's the algebra portion. So we prove our identities using the definitions of what we have created. And algebraically, they work out. Okay, 15 minutes left here. We still jamming. Let's do a derivative. Can we? Are we good there with this one? And any questions on this so far? We just kind of just did an algebra proof, basically, that they're both the true. Or we basically, it says proved an identity. So we didn't solve an equation, right? Solving means we move from one side to another, right? Proving identity, which means we start off right side and left side equal each other eventually. Okay, let's do a derivative. Find the derivative of sinh. Let's do this one together. And you'll see like, oh, that was kind of cool. So the derivative of sinh, we move back to definition. And the definition of sinh is?
dx minus the negative x over 2.
Perfect. Okay. That is the definition. And then do we know how to take derivatives of e to the x?
Mm-hmm.
Yes. Because we have a 2 on the bottom and not a 2x or any variable, right? We can treat the 2 as a constant. We good? So really are just taking derivatives at the top. Are we good? If we wanted to, we can actually move the 2 out and make it a 1/2 multiplier, right? So we can leave it there. So really we're just taking derivatives of e to the x and e to the negative x. That's all. What is the derivative of e to the x? E to the x. What is the derivative of e to the negative x? Perfect. It is e to the negative x because it's own derivative, right? And then what's the derivative of negative x? -1. Perfecto. So then we get something that looks like this. So by definition, what is this? It's cosh. Absolutely. So there it is. We just proved the derivative of sinh is cosh.
Definitely negative sinh.
Oh, okay, cool. Okay. So Luke says it's probably negative sinh. And remember let's see, a derivative of cosine is negative sine. Is that right? For us? Okay. Let's see if it does. This is how we look at our intuition, and this is how we compute it to see if our intuition's correct. This is cool. Yeah.
I don't get why we left the two, like, I know that it works, but like, I don't know.
Oh yeah, because it's a constant, we could have actually even moved it out and being like a multiplier of one front, because we didn't care.
Take the derivative.
No, and the reason for it is kind of like
Well, product rule makes it so that it all like cancels out.
yeah, let's see,
1/2 times the derivative of dpx plus
Yeah.
the derivative of the variant half plus e to the x, so equals 1/2 e to the x plus the derivative. So
if you take, yeah, is that good? That makes sense. Yeah, so we can leave it out front. Whenever we take a derivative of x cubed over 2, we don't care about the 2. We just take derivative of that, right? So the 2, because it's a constant, does not affect anything for us. But good job. Yep. Okay, here it is. By definition, e to the x plus e to the negative x over 2. Is that right? All right, let's take the derivative of e to the x is e to the x.
interesting.
Oh, interesting. It's that. Is that right? By definition, what is that?
It's just the sine cinch.
Cinch. It is just cinch. It is a cinch. Cool. Okay, so that's weird. So with the regular cosine functions, right? It goes sine goes to cosine, cosine goes to negative sine goes to negative cosine. These guys, they just switch back and forth, right? Cinch goes to cosh, cosh goes to cinch goes to cosh again, and we keep on going. Interesting. Okay, so there's a little bit of a change there. And then we just actually found 2 definitions, right? If we kept on going, here are your other definitions or derivatives. Sorry, derivatives. Listed derivatives, I guess I should say.
Wow.
10 minutes. Okay, so let's go with
Ben and Jerry. Ben and Jerry. X and Y.
all right, if you want to write them down, that's perfect. They are in your textbook as well, right? So you have them. And you probably, at this point, even I do. I'll have to look them up. If I'm taking derivative of hyperbolic secant, I'm like, let me look that up. Good. Not something I've memorized. All right, so these are the formulas that you guys have on your derivative sheet, right? It's like all those like 33 formulas we have. This is part of them. All right, so let's see. Guys, let's talk about this here. So remember when we looked at derivatives, there was a product rule, quotient rule. So chain rule, is that right? So we're going to do all of those things all over again, right? Just with the hyperbolic functions now. So it's like, can you take a product rule with hyperbolic functions? Can you take a quotient rule? Or can you do a chain rule? Just for simplicity's sake, we'll just do a chain rule real quick here. So if you guys, can we take derivative of this? All yours. Work with it, work with the person next to you. See if you guys can do that. The only problem that would happen is Luke, because White's not next to him anymore. So can't check with the person next to, but maybe you can actually ask Adrian or something.
The product rule. You want to look inside the sine of H.
It is. Let's see. What's the? It's just chain rule, right? We'll go from outside in, right? Like peeling an onion. Here it is. So what's the outside function here? It's cosh. The derivative of cosh is Cinch. Everything else remains the same. So that, and if we want to, we can make that square root to be a 1/2. Is that right? So 1/2 is the inside function, cosh is the outside function. Peeling an onion says cinch, and the stuff inside stays the same. Is that right?
Oh,
Then what is the derivative of x to the 1/2? Perfect. Yeah. 1/2 x to the negative 1/2 or over 2. And then eventually we do want to put them back into radical form because this is called exponential form. So let's go with cinch square root of x. It's there. Let's see what else we got. We got a 2 on the bottom because that little 2 1/2, right? And then we take that x to the negative 1/2, we take it down to the bottom to make them positive 1/2. Is that right? And then we still put it into radical form. So there it is. Okay, so how come you can't just chop off the square root of x's on top and bottom?
Because it's inside.
Perfect. Yeah, that radical x is inside cinch, right? This is part of this function, so can't do that. Okay, are we good? Okay, 10 minutes left. Let's do one more thing here. That's so cool. So in trigonometry class, do you guys remember we defined the trig functions? What else did we define in trigonometry class? We defined 6 more other functions. Do you guys know the name of them? There was the trig functions, and then there were the inverse trig functions. Oh man, so in trigonometry class last year, we actually had 12 functions. Is that right? Okay, but this stuff works exactly the same. So if I were to make, so here's what it kind of looks like. Kind of weird at first here. We take this function right here, right? Oops. And we flip the x and we flip the y, and it looks like this right here. Then we try to model that function. Are we good there? Looks kind of weird at first, doesn't it?
They just put the.
Sure. Let's go. To make an inverse function, here's what you do. You switch the x's and the x's across each other, like this.
oh, that's weird. Oh, and you flip it. No.
And then you rotate it. So now you have positive x's here, is that right? Still you have positive y's here, right? So then what you do is you rotate it like this. So now notice what you have is you have positive y's here, positive x's here, negative y's going this direction, and negative x's going this direction. Ooh, guys, sorry. It's going to be like a crushing brain crush here. Just like it is the last section of chapter 3, right? So this is like, it's the last section of each chapter. It makes it a little more difficult. The question is, what are inverse functions of exponential functions? Logarithmic functions. Remember those from algebra 2? The opposite or inverse of exponential is logarithmic. So we're going to get some logarithmic formulas here. So this guy here, the question is, what is the model of this? Now we're running a little bit at a time. So can I just give you guys just one of them? We're good? And then, so here's your, wow, look at that. This is called a hyperbolic, so inverse cinch. We good? That's what it looks like right there. What is the algebra formula for it? And let me just see. Let's just copy down cinch. We good? You guys have the other ones in your book. We good? But just if you guys can copy down, there it is. It's a ln function. So inverse cinch is ln of x plus the square root of x squared plus 1. This is getting crazy.
I don't like our inverse chicken. Please don't make us do more homework with this. Please.
There's just a little bit, not too much here.
So it's the x.
This is a buildup, so I'm not going to have you guys do. I don't think there's any algebra with the inverse functions, but we want to take derivatives of that. So then the question is, if we have a graph that looks like that, go ahead.
Excellent.
Oh, element of. So x is an element of the real numbers. It means x is a real number, as opposed to like x would be only integers. Then it would say x is an element of the integers. So have you guys ever seen a symbol before, the little E? No, interesting. Okay, gotcha. I think I did it one time where it was like X is an element of quadrant one. Remember when we used to do those? Instead of saying X is in or theta, right? Theta is in quadrant one. I used to say theta is element of quadrant one. So it's within that scope. Okay, we don't need to know the algebra of it. We do develop all the trig formulas, and then we could do it just like we did for the sinh function, right? We just put the definition in. We take the derivative of ln of blah, blah, blah. That's crazy to do. Not going to do it. We good? But then if we did do that, if we took the derivative of inverse sinh, which is the derivative of this, and we do a whole bunch of work, the question is, what does it come up to be? And the interesting thing is, it comes up to be like this. Just that little weird thing here. So the derivative of inverse sinh is 1 over the square root of 1 plus x squared. Okay, don't need to write that one down. For our purposes, can you guys write down just inverse hyperbolic tangent? Just that one there. So let's practice with this one. On the next slide, we'll practice with this one. So the derivative, and you guys have all the rest of them in your book. And if you ever want to sort of see them, if you flip to the back of your book, here's your derivative formulas. There are 36 derivative formulas. And notice, bam, this is the last one. There's your hyperbolic trig functions. There's your inverse hyperbolic trig functions. So that is the end. We got to 36 and we're at the end. So that's why we're at the end of chapter 3, because now we're going to turn around and we're going to start applying them.
It's sure going to be so much fun.
Absolutely. So can you guys, let's see, with 3 minutes left, can you guys give me the derivative of hyperbolic tangent inverse of sine of x? Whoa.
No.
So let's go with it. So here's our formula. So the derivative of hyperbolic tangent would be 1 minus 1, and then we keep this the same for now. Is that right? Right, so it's this x here with this x over here. It's just going to be the square of whatever this x was. Good? So we're gonna square it. And then, of course, we've got to take derivative of the inside. So let's do that here. So if it's this part means 1 minus, or 1 over 1 minus the square of your inside function. Everybody okay there?
That's just like a definition.
Yeah, so by the definition, it's whatever the x was, that's what you square. In this case, it was sine of x. So we're going to square sine of x. And then we take the derivative of sine of x. What is the derivative of sine of x? Cosine of x, absolutely. And then can we simplify? That's where the rubber meets the road with calculus here. It's all the algebra stuff that you know, or the trigonometry stuff that you know, that you can simplify. So let's see, I'm going to go with 1 over 1 minus sine squared x. Is that right? What is 1 minus sine squared x? Cosine squared x. Absolutely. So we have now cosine x over cosine squared x. That's the Pythagorean theorem, right? Right there. The trigonometric Pythagorean theorem identity. And then what is cosine over cosine squared x? Which is secant. We good? There it is.
Yes.
Are we good? Mm-hmm. And that's the end of the lesson. Cool. So, guys, we are at the end of chapter 3. We are done.
All of them. Let's say for